enhancing the stability of pit soil through treatment with pond ash hydrated lime under varying soaking durations. Introduction: Pit soil presents challenges for civil engineering due to its high compressibility, water content, low shear strength, and settlement issues, making it unsuitable for infrastructure. To improve its suitability, hydrated lime and pond ash are used for stabilization. Hydrated lime is a widely available stabilizer, and pond ash is an eco-friendly byproduct. Combining hydrated lime and pond ash can effectively address ground settlement problems in pit soil. This study's objective was to modify pit soil by binding pond ash and hydrated lime together and to investigate the effect of this admixture on the strength of the modified pit soil. Methodology: In this study, five physical properties tests including moisture content, specific gravity, organic content, fiber content, and pH test, and also one engineering properties test, which is unconfined compressive strength (UCS), were conducted in this study. All tests were performed according to the British Standard Method of Test 1990. Table 1 shows the summary of laboratory tests executed. Moving on to result and discussion. For physical properties, this study found that peat soil has an average moisture content of 811%, reflecting its high water holding capacity. This is due to the soil's organic composition, including partially decomposed plant material and intact plant cells. The high moisture content influences the soil's engineering properties, such as compressibility, shear strength, and permeability, which are important for soil stabilization, land use planning, and environmental conservation. Peat soil has a relatively low and variable specific gravity of 1.36, primarily due to its high organic and water content and low mineral content. This value can vary depending on the degree of organic matter decomposition and the type of vegetation that formed the pit. This study found that the soil had an average organic content of 98.8%, characteristic of the pit soil. Despite the high organic content, the specific gravity value of 1.36 is not significantly different from that of mineral soil. This study also found an average fiber content of 92.29%. Identifying the botanical origin of peat base and on fiber content is difficult, especially with highly decomposed peat lacking recognizable plant structure. Additional methods may be needed for accurate identification. Lastly, this study found that the average pH of the pit soil was 3.52, indicating high acidity. This acidity may be influenced by seawater drainage and nearby pineapple plantations, where fertilizers and chemicals could contribute to the soil's acidic pH. Result and discussion for mechanical properties. Focusing on maximum stress value shows the treatment's effectiveness over time, but plotting complete stress strain curves for each sample at different soaking times would offer a deeper understanding of soil behavior under various loading conditions. The strength of the treated pit soil increases with the addition of hydrated lime and pond ash, as shown in all samples. Figure 1a illustrates this, with strength rising as the pond ash hydrated lime content increases up to 50% of the original pit soil. For samples soaked for 7 days and 14 days, as depicted in Figure 1 and Figure 1b and Figure 1c, respectively, the strength continues to increase, reaching represent approximately higher strength of soil. This considerable increase in strength underscores the effectiveness of the treatment method involving hydrated lime and with pond ash. The incorporation of sample resulted in significant enhancement in characteristics, rendering it more suitable for various engineering applications. The significant increase in strength after soaking the samples for 30 and 60 days as shown in Figure D and E is remarkable. Figure 1D shows a strength increase to 167 kilopascal, 7.6 times that of the untreated sample, while Figure 1E shows an increase to 188 kilopascal, approximately 8.5 times the untreated sample strength. This increase can be attributed to soaking, which enhances hydration in materials like concrete. The soaking process allows water to penetrate the material, completing the hydration of cementinous components, resulting in stronger bonds between aggregates and the cement matrix. Additionally, soaking can reduce material porosity, making it less susceptible to damage from external factors like freeze-thaw cycles or chemical attacks, thus improving overall strength and durability. These findings highlight the importance of soaking time in assessing the strength and durability of construction materials, suggesting that longer soaking times can significantly enhance strength characteristics. Next, in Figure 2, Sample 1 shows an interesting trend in strength during soaking. Initially, there are increases of 18%, 102%, 4%, and 32% at different stages. However, at 28 days, strength drops by 43%. Despite these fluctuations, the strength reaches a maximum of 91 kilopascal after 60 days. Complex interaction between pond edge content, soaking duration, and resulting strength. Analyzing these trends can provide value insights into the material's behavior and guide its applications in construction and other industries. In Figure 3, Sample 5 and 6 initially showed strength increases of 42%, 60%, 7%, and 47% before a slight 6% decrease. At the 60-day mark, strength increased significantly by 69%, reaching 141 kilopascal for Sample 5 and 147 kilopascal for Sample 6. Afterward, Sample 5 experienced a minor 1% decrease followed by a significant 40% drop, then rebounded with a 71% increase. Concurrently, Sample 7 showed a substantial 79% increase, reaching a maximum strength of 158 kilopascal. This complex relationship between soaking duration and strength development suggests variations among samples and indicates a need for further investigation. In Figure 4, Sample 9 shows an early and consistent improvement in strength during soaking, increasing by 13%, 28%, and additional 40% at different stages. This positive response highlights the effectiveness of the soaking process in enhancing strength. Understanding this trend can help optimize soaking techniques for similar samples in future applications. Meanwhile, in Figure 5, Sample 13 initially shows a slight 3% decrease in strength. However, at the 60-day mark, strength increases by 39% and remains consistent thereafter. This indicates that despite an initial dip, the soaking process leads to a significant and sustained improvement in strength. Understanding this pattern is crucial for optimizing the soaking process and ensuring consistent strength characteristics in similar samples. Further analysis could reveal the mechanism behind this improvement and help refine soaking techniques for better performance. The research aimed to stabilize speed soil by mixing it with varying percentages of hydrated lime and pond ash, then soaking the mixtures for 60 days. And confined compressive strength tests evaluated the effects of pond ash and hydrated lime. The following concentrations were drawn. The average moisture content was 811%. Specific gravity was 1.36, low due to factors like organic and water content. Organic content averaged 98.8% and fiber content was about 92.29%. The soil's pH was 3.52, indicating high acidity, possibly from saline water or nearby plantations, and combining hydrated lime and pond ash significantly improved compressive strength, with a 39% increase after 60 days. Thank you.